Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. We'll continue with section 7.3 operations of EIGRP. This is part of chapter 7 EIGRP. CCNA semester 3 scaling networks. Now the goal of any dynamic routing protocol is to learn about remote networks, reach convergence in the routing domain, and then to establish and maintain EIGRP neighbors adjacencies. EIGRP router will use the hello packets, and it will use the metric parameters must match. We'll talk very soon about it, and the AS number must match. So when we exchange our hello packets, we check all these parameters. Do our metric parameters match, and does AS number match? So think about this network. We have router A connected to router B. So router A sends a hello message, says I'm router A, who is in the link. Now router B automatically adds that to the routing neighboring table. Says yep, potential neighbor. Sends a hello back saying yep, hello, I'm router B. And router A will add that router on the neighboring table. Router B will send all the complete route information they has. Here's my complete routing information. And router A will acknowledge that. Says okay, I got that, thank you very much. Then router A will add everything on the topology table. They will send his own update, complete routing information. Router B will acknowledge that, and it will add everything they learned from router A on its own topology table. Then they will run the algorithm, find out the best path, loop-free path, and they will put it on the routing table. Now the network is converged. Very simple, much more simple than it was when we were talking about OSPF. So EIGRP metrics. EIGRP uses the following values in its composite metric to calculate the preferred path to a network. So we have bandwidth, and here we pick the lowest bandwidth between source and destination. So like I said, if from the source to destination it has to go like from A to B is 100 Mbps, from B to C is 50 Mbps, from C to D is 100 Mbps. We ignore the highest ones. So we ignore the 100 Mbps. We pick the lowest on the path. Then we look at delay, the cumulative interface delay along the path. So delay is added from every source to every path that we go, to every hop that we go, we add the delay. And we can look at reliability, worst reliability between source and destination based on the keeper lives. Load, worst load on a link between the source and destination based on the packet rates and the configured bandwidth of the interface. And we can look at the MTU as well, but although MTU is included in the routing table updates, it is not routing metric used by EIGRP or IGRP. So the composite metric, by default, composite metric, we look at K1 and K3. So only K1 and K3 are taken into account, which are set to 1. So K1, which represents our bandwidth, is set to 1, and K3, which represents the delay, is set to 1. K2, which is load, is 0, we're not calculating that, and K4 and K5 are 0 as well. So for example, if you want to change the metric weights, you have to go to the EIGRP routing configuration and say metric weights toss, that will be the 0, and then you change the values K1, K2, K3, or K4, or K5, whatever you want to change. But you have to remember that they have to match. All the neighbors, they have to have the same K values. By default, we have K1 and K3 is already set. The result is the only bandwidth and delay values are used in the computation of the default composite metric. To verify the K values, we do show IP protocols, and we can see that weight values of K1 is to 1, K3 to 1 as well. So only we're using bandwidth and delay. For example, you can even go further here. For example, if our delay is more important than our bandwidth, but we still want to calculate the bandwidth, we can put K3 equals 2. So that's going to be more important. We check the delay. Or K1 equals 2. So it doesn't have to be 1, just 1 only. The K values on R1 are set to default. Changing these values to other than default is not recommended, unless the administrator has a very good reason to do so. So examine the metric values. For example, show interface serial 000 is going to show us all those K values what we could be using. Show interface command lets you examine the actual values used for bandwidth, delay, reliability and load in the computation of the routing metric. Default values, we have a bandwidth 1544 kilobits, and then we have a delay represented in microseconds. So the bandwidth metric is 1544 kilobits per second. It's a static value used by some routing protocols, such as EIGRP and OSPF, to calculate the routing metric. It's in kilobits per second. Most serial interfaces use the default bandwidth value of 1544 kilobits per second, or 1,544,000 bits per second. The value of the bandwidth might or might not reflect the actual physical bandwidth of the interface. Modifying the bandwidth value does not change the actual bandwidth of the link, and should reflect actual bandwidth of the link. Delay is measurement on the time it takes for the packet to traverse a route, based on the type link or the interface. So, expressed in microseconds, millionth of the second, the router does not actually track how long the packet are taking to reach the destination. Like the bandwidth value, delay is a default value that can be changed by the network administrator. Default value is 20,000 microseconds for serial interfaces. So for serial interfaces we have 20,000 microseconds, 100 microseconds for fast Ethernet interface. You can see it here. Reliability, this is optional metric. Reliability is a measurement of the probability that the link will fail, or how often the link has experienced errors. Values are, you can put from 0 to 255. 1, a minimal reliable link, so for a bad link. 255 is 100% reliable link. By default, the EIGRP does not use reliability in its metric calculation. Load, again, another optional metric. It reflects the amount of traffic used in the link. Values from 0 to 255. A lower load value is more desirable because it indicates less load on the link. 1 to 255 would be a minimal loaded link, so 1. 40, a link is 14% of the capacity. 255 will be the 100% saturated. By default, the EIGRP does not use load in the metric calculation. Using the bandwidth command, most serial links, the bandwidth metric defaults to 1544. Correct values for bandwidth is very important to the accuracy of the routing information. So bandwidth command modifies the bandwidth metric. No bandwidth will restore it to default. So for example, we have to go in the interface and we configure the bandwidth. For example, on router 1, 64 kilobits per second on this serial interface. We have to do the same for router 2. So their neighbors, both, they have to configure the same values. And between router 2 and 3 is 1024 kilobits per second. So configure the bandwidth commands for router 1 and router 2. So we go router 1, on that interface bandwidth 64. On router 2, same interface, well, same link here that we have, for 64, bandwidth 64. On router 2 again, for the interface between router 2 and 3, 1024, and same thing we do it for on router 3. Modifying the bandwidth on the appropriate serial links or interfaces. Verifying the EIGRP bandwidth, it is important that the bandwidth parameters are the same on both sides of the link to ensure proper routing in both directions. So that will verify that we have configured our bandwidth to 64 kilobits per second. And then we do the same for router 1 and router 2, make sure that they have the same values. Metric calculation, using the default value for K1 and K3, you can simply simplify this calculation to slowest bandwidth, that's a minimum bandwidth on the path, plus cumulative sum of all the delays. That will give you EIGRP routing metric. So for example, show interface, we see the bandwidth is 1024 on this side, and the bandwidth here is 1 million. So we're going to ignore this fast link. We're going to just take care of this slow link. So 1024. So we can look, okay, calculate the bandwidth using the slowest bandwidth to the destination. So to the destination, we show IP interface until we find the slowest link. We pick that slowest link and we use a formula which is 10 million divided by 1024. and it will give you the digits, 9765. We keep that on the memory because we have to add the delay. So 9000 is rounded to 9765. So bandwidth is 9765. Some of the delays now. Delay is represented in microseconds. So 20,000 plus 10 is 20,010. So 20,010 divided by 10 will equal to 2001. So our delay is 2001. So we have to add delays as we go, but we have to divide it by 10. So slowest bandwidth plus the sum of delays times 256 is a formula. Use the result of default metric. So we have bandwidth plus the delay times 256 is our metric. So bandwidth was 9765 plus the delay 2001 times 256 will give us 3,012,096. That will be our metric. I hope this makes sense. So you really have to do it on a piece of paper many times until you understand it. What we're talking here, so the link from the source to destination, you look at the bandwidth, so show interface, whatever, all the interfaces, and find out the slowest link. Then that slow link, the slowest link, you use a formula 10 million divided by the slowest link. Whatever the number it gives you, you keep that in the mind. So 9765 here. Then the delays, they're represented, we look at the delays as well. So, but the delays are represented in microseconds. What you need to do, you have to add all of them and then divide it by 10. So 20,000 plus 10, 20,010, divided by 10, 2001. So that's our delay. And then you can use bandwidth, which was 9765, plus delay times 256. That will give you the metric. So dual concepts. Diffusing Update Algorithm is an algorithm used by EIGRP, which determine the best loop-free path. Loop-free backup path, so which we can use immediately. If our best loop-free path fails, then we can use the backup immediately. Dual also provide the following: fast convergence, minimum bandwidth usage with a bounded update, because after we exchange our topology, then we really don't tell anything unless something happens, unless something changes. So EIGRP is very quiet protocol. Just keep sending hello messages, unreliable hello messages, and everything is fine. When something changes, then we send a bounded update. Dual uses several terms that are discussed in more detail through this section. We talked these ones. Successor, we need to find out what it is. Feasible distance, feasible successor, reported distance on feasible condition. So, concept, for example, think of this network. Network 10.0.0.0, this topology here, we have RX, router 3, and router 1. RX is connected to network 10.0.0.0/8. Now R3 is reporting to R1. He's saying, if I can get you to network 10.0.0.0/8, the metric that I can use is 100. It costs me 100. This is what router 3 is telling router 1. Okay, so router 1 thinks, okay, great. I can go to network 10. It's 100 from R3, but I need to add whatever it costs me to get to the R3 as well. Now we get another neighbor says, I can get you to the same network, but it costs me 300. Now router 1 says, okay, well, I need to choose, do I go through router 3 or through router 2? I will choose router 3 because router 3 has got less. It says advertising 100 and you are advertising 300, so I'll choose router 3 as my best path. And it costs me only 20 to get to router 3, so in total my router is 120. My feasible distance is 120. Router 3 reported distance is 100. So router 3 is reporting 100. I'm adding my 20 they cost me to get to router 3, so my feasible distance is 120. Now router 2 is advertising at 300. But because his reported distance is higher than feasible distance, this is not going to be my backup route. Why? Because router 2 could be coming through router 1 to get to the destination. There could be another path towards router 1 to get to the destination. So for that reason, because there could be a loop there, you are not going to be as a backup. Now think of the same topology router 3 is advertising and saying, okay, well, I can get you to destination and the metric is 100. Now router 2 is saying, okay, the metric is 110 through me. My advertised distance is 110. Router 1 will choose router 3 because it's got a lower cost. 100 is lower than 110, including my cost to get to the destination, so 120. But this time now, is router 2 going to be my backup path or not? Well, yes, because there's no way, if he's reporting 110 and mine is 120 to get the destination, no way he's coming through me, because if he's coming through me, there's going to be more than 120. So for that reason, this will be a backup path, definitely, because it's going through another way to get to the destination. So for that reason, this is how our EIGRP uses Joule to have a loop-free topology. Finds the best path to the destination. From me to the destination, it's called feasible distance. Now, if you telling me something, you get another router is telling you how to get to the destination, that's called the reported distance. And I compare that reported distance with my feasible distance. So if your reported distance is less than my feasible distance, I know for sure they're not coming through me. So that's a loop-free, and you can be as a backup path. So EIGRP is a distance vector routing protocol. It does not see the topology map, so I can't tell if there's a loop or not. To play it safe, EIGRP only accepts a backup route if it meets the feasibility condition. Router 1 will only use router 2 if router 2 is metric to the network is less than router 1 cost through router 3. So a successor is a neighboring router that is used for packet forwarding and is the least cost route to the destination. That's going to be the successor. So the cost the least to get to the destination, then you're the successor. So R2, for example, to get to the destination is using R3 as our successor. Successor's IP address will be on the routing table. So R3 is my successor for getting to the network 192.168.1.0. That's a feasibility distance. That's how much it costs me. That's a metric. So feasibility distance is the lowest calculated metric to reach the destination network. The metric for the route. R1 is a feasible successor, like a backup, right? Now, does R2 know if R1 has a loop-free backup path to the same network? Well, remember EIGRP is a distance vector routing protocol, so it doesn't know is it loop-free. A feasible successor, FS, is a neighboring who has a loop-free backup path to the same network as a successor, as long as it's satisfied in the feasibility condition. Feasibility is my feasibility condition means the feasibility distance. What's the feasible distance to get to the destination? As long as your advertised distance is less than my feasible distance, then you do satisfy the feasibility condition. Would router 2 consider R1 to be a feasible successor to the network 192.168.1.0? To be a feasible successor, R1 must satisfy the feasibility condition. Now, send the reported distance. So this is what R1 is telling us. It's reporting, I will send R2 my feasible distance. So R1 is sending their feasible distance to reach that network. For R2, that is considered reported distance. So the reported distance is 2,170,112. That's their feasible distance. So don't get these words mixed up, because there's so much feasible distance, feasibility condition as well. But the reported distance is what your neighbor is telling you to get to the destination. The router 1 and router 3 reported distance to router 2. Router 2 picked the best one, and that's a successor. And then to find out the backup is, as long as you report in less than my feasible, then you're my backup. The reported distance, or advertised distance, EIGRP neighbors feasible distance to the same destination network. The metric that router reports to neighbor about its own cost to that network. Feasibility condition is met when a neighbor reported distance to a network is less than local router feasible distance to the same network or same destination. So does R1 meet the feasibility condition? Well, that's my feasible distance, 3,012,096. That's the successor. And this is what R1 is reporting 2 million. So obviously R1 does meet that condition. So feasibility condition is met when a neighbor's reported distance to network is less than the local router's feasible distance to the same destination. So R2 feasibility distance to that destination is 3 million. R1 is reporting 2 million to that destination. So R1 reported distance is less than R2 feasible distance. So yeah, R1 will meet the feasibility condition. So that's when we do using the feasible successor as a new successor. So feasibility distance, now if we lost that network, we will go right away and we switch to the next router who was our feasible successor. And then we can show IP route, we have a new metric. So R2 is topology table. If we do show IP EIGRP topology, here we can pretty much see everything from this, what is the successor and so on. So we were going to concentrate on one network, so let's pick that network from the topology. So first, the code. Passive, P, means it's good. Passive is like, okay, everything is cool, everything is working, so it's fine. Active means okay, there's a problem and we actively trying to find out there's an update, there's another path to destination. We can have an update, so we're updating. Query, we have queried. Reply, R, reply the status, or S, stuck in status, or SIA, stuck in active, sorry. Okay, so this is the network that we're going to look in more detail now. So we look at 192.168.1.0/24. It says one successor, and feasibility distance is 3,012,096. So indicators, P indicates passive. Okay, everything is cool, it's working. That's a destination network, 192.168.1.0. How many successors we have, and what's our feasible distance? Okay, the successor is the next one underneath it. The next hop addressed to the successor, that's a distance, a feasible distance from us to the destination, to that destination, whatever we are configuring or we are trying to get to. That's feasible distance. This is what they reported. What is the neighbor or successor reported? 2,816 to get to the destination. Well, that's called the reported distance. This is the outbound interface I will use to reach that network. The feasible successor information is underneath that. So we have only one successor. So first line, the top line, that's our successor information. Then you could have more feasible successor underneath. Next hop address of the feasible successor. So if the successor goes down, then we'll have a feasible successor that we could be using. That is our feasible distance if we use the feasible successor. Alright? So to the successor is 3 million. If we go through the feasible successor, it's 4 million. So primary 3 million, backup 4 million. This is what they're reporting to us, 2,170,000. Because they're reporting 2 million and our is 3 million, our feasible distance, for that reason we know it's a live free. And this is the interface, exit interface, if we want to use them. So the reported distance is less than feasible distance, so yeah, router 1 is our feasible successor. No feasible successor. So for example, if we don't have that feasible successor example, you can view all possible links, whether they satisfy the feasible condition or not, by adding all links there, right? Even those routes that are not feasible successor, they will display. That, for example, show IP EIGRP topology, all links. Now you can see that router 1, to get to the destination, has got 2,170,112. That's a feasible distance. That's a serial number 9. Okay, that's not important here. Because I get lots of questions, oh, what was this? That's not important. All the other information is important. Now, that's our feasible distance. This is what the neighbor is reporting. The router 2, 172.16.3.2, is reporting 3,012,096. Since that's higher than our feasible distance, then there's not going to be a successor. Feasible successor. That's our successor in red, but in blue, it's not a feasible successor. So is R2 a feasible successor? Does it meet the condition? No, because R2 is reporting higher the feasible distance. they are reporting their feasible distance higher than our feasible distance, which means they could be coming through us to get to the destination. So it does not meet the feasibility condition. Even though R2 looks like a viable backup path to the 192.168.1.0, R1 has no idea that this path is not a potential loop back through itself. Does this mean that R2 cannot be used as a success if the successor fails? No, it doesn't mean. R2 can be used, but there will be a longer delay before adding to the routing table, because we run again the dual, we'll find out a new successor. So if we lose that, we still will use that. We'll use the new successor, but it's just how we run through the algorithm again. Before this can happen, the dual will need to be some further processing, which is explained in the next topic. So, dual finite state machine is if you've lost connection to the successor, you don't have the successor anymore. What do you do? Alright, let's go. Is there a feasible successor? Is there a backup? If there is, I will promote that backup or that feasible successor to be my new successor. And I will install that successor in the routing table, select the new successor, and then install feasible successor if we find any new feasible successor. If there is not a feasible successor, then place the destination in the active. Place the destination network in the active states, so change that P to A, and query our neighbors. So we send the neighbors and say, okay, well, do you know I lost this route? Neighbor has one or more routes, then that's it. Select a new successor, great. If the neighbor doesn't have, we will remove the destination network from the topology in the routing table. Thank you very much for watching my video, and hopefully to see you in the part 7.4 EIGRP for IPv6. Thank you very much, and bye bye.